continuous spin unless an outside force is acted on it, and is also a vector quantity, which who knows what a vector quantity is? Yes?
It has direction, a definite direction.
Okay. And if it's a spinning object, do you know which way would it be?
So for a spinning object like this, which direction will the vector be for, let's say, angular speed?
Clockwise?
Let's see, for you guys, it is going clockwise, but the vector will actually be pointing toward me.
Yep, it's the right hand rule. It wraps your fingers wrap around the direction that it's spinning in, and then your thumb points in the direction that the vector is going in. And here is an example of how this is applied.
Today on Secrets of Skating, I'm talking about the scratch spin. So
Nancy Kerrigan?
Make the audience balance because you can make it so fast and exciting. What the judges are looking for in a test or a competition is the circles, how tight they are actually on the ice. It's very exciting for your audience to watch, and the way to make it very fast is the centrifugal force of the arms. Like ballet dancers, they keep their arms in front of them a little when they start. To make it fast, you bring your arms closer and in tight, and you can either go way up or down, but when you do that, you need to keep your arms right over your shoulders or right close to your body, and that makes the spin faster. For instance, if you're spinning with your arms wide and your feet wide, the more you pull your arms and your feet in, that's what makes the speed.
Secrets of skating.
All right. And as we learned yesterday, these are equations. Can anyone tell me what I stands for? Heard it a little louder?
Moment of inertia.
All right. And moment of inertia is also represented in both of these ways. This is more broken down because momentum is mass times velocity. And omega, the funky looking W, is, a moment of inertia is measure of an object's resistance to change in its rotation. And omega is the angular speed. And angular speed is different from regular speed just because it is rotating. So it has a different representation for it. And as we learned, moment of inertia there's different equations for depending on what the object is, if it's hollow, if it's solid, if it's cylindrical, or a hoop, or a sphere, or a rod.
All right. Wheels or other rotating objects will have kinetic energy. An object that's spinning will have rotational kinetic energy. As you see, it's moving, but it's not moving in the way before where we have it going horizontally, which is the kinetic energy you learned about in probably chapter 4 or 5 of the book. And this is going to be very close to the equations that we have for normal kinetic energy, except for it'll be in rotational terms. So, the way we define rotational kinetic energy is up there. It's the energy due to an object's rotation. As you know, there's different energies. Kinetic and potential is so far what you've learned. Gravitational potential energy is the only potential energy that you know, but you also know translational kinetic energy and also rotational. Rotational kinetic energy will be zero, just like regular kinetic energy if it's not rotating. Even if it's rotating a little bit, which I see it's rotating very, very slightly, it does have rotational kinetic energy. Also, energy is a scalar quantity. It is not a vector quantity. So it doesn't matter what direction it's spinning, it has just a positive energy. These are the two equations we have. As you can see, that's why rotational kinetic energy is always positive. One half is positive, I is always positive, and any number squared, as long as it's a real number, will be positive. There's two ways to represent that. It's I omega squared, which is the moment of inertia times angular speed squared, and then there's also angular momentum squared divided by I. Both are equivalent. Conservation of energy. So, just like in normal energy before, we've learned that energy is conserved, as long as there's no non-conservative force acting upon it. So, with wheels and other rotating objects, we actually find that we have less non-conservative forces at play. While here there is still non-conservative force at play, which is on the axle here, the wheel is spinning, there is going to be some slight friction. But if I would roll this, I want to clear a little layout. If I would roll this, it doesn't slide. Initially it did slide a little bit, but once it started moving, it didn't slide. And then we'd have no non-conservative forces, which is good because a lot of stuff that has rotating objects means that energy is conserved. So if we roll something down the ramp, energy conservation will be true. And that's what we're going to do later today. Our goal for today will actually be to find a moment of inertia of an object that isn't one of the common ones. As you saw before, we had that table of a moment of inertia of common moments of inertia. What about something like the human body, the chair, other things like that? How do we measure their angular momentum? Moment of inertia, which would help us calculate their angular momentum, also the rotational kinetic energy. So, in the lab today, we will split you into two groups. One group will be measuring the moment of inertia of a wheel, similar to this. While we could make an approximation for it, measuring its mass times r squared and using the appropriate equation for a hoop, it's still going to be slightly off. So what we're going to try to do is experimentally measure it. We will also calculate it using equations, but experimental and theoretical, and see what we would get. All right, so I think the easiest way will just be to split you guys down the middle and have half of you go with Hanna here.
This half can go to the far end on the right, and this half can come right here.
The front of the blue tape to the front of the blue tape.
23.5 centimeters.
All right, ready?
And I'm counting every time it comes.
Yep, so you're gonna.
Oh.
So it'll get spinning.
I'm in a second.
Yeah, it's 66. I got 65. Yeah, we have.
All right, so we're really close. So well, let's run this more than one time.
Is your measurements, it's not in seconds, what is it, point something seconds?
It's not a second.
0.6 seconds, okay.
Angular speeds out there. Now I said the goal of this lab was to calculate the moment of inertia using conservation of angular momentum. So if you remember to the ramp part, we used conservation of energy to get the moment of inertia of the wheel. We would use conservation of momentum to get the moment of inertia of the person spinning out there. So when you had the wheel, you turned it. Initially there was no angular momentum in either in the vertical axis. But once you turned it, there was, and that's what caused you to start spinning. So
for 20% error, but I really
we can switch now. They have got all the
So, using the calculation from the hoop and approximating the inertia gives a similar result, although it's about 25% off compared to the experimental. I wonder how the experimental would work if people were drunk.
Ideally, what we're going to try to do is we're going to need one person to get this spinning while she's holding it out. And then what you're going to do is you're going to go like this and make it around hopefully one time. That's what we were having trouble with in the last group. So we'll need somebody to time how long it takes for her to make one rotation around. Alright, and then you see this piece of tape? How many times? 5 times. So you might have to move around with her. Like how many times the tape passes you 5 times.
Okay.
So like
5 rotations
like
of the wheel.
5, stop.
Okay.
Yep. And you can try to count as it passes by because it might be hard for him to see.
yeah.
But like 1, 2, 3, okay. And who would like to spin her? Spin her wheel.
Spin me nice.
Yeah.
I can spin her wheel. So which
Okay.
way?
So either way, you can just get it started going really well, and it might work if it seems like you're not moving. Otherwise, just flip it to the other horizontal.
Alright.
And so the stopwatches will start when it goes horizontal.
Gotcha.
Alright, ready? Yeah. Go.
All right. I have to get spinning a little more. Yeah. So then you want to just count out loud.
It's hard to get it going. I can't see the tape either.
4, 5. Yep, straightly above your head. There you go.
Elegance.
Beautiful.
Yeah.
I want to try it.
I've done it, yeah.
That's
Someone else
good
did
grace
it.
right there.
His ending wasn't too bad there.
I had a lot of practice doing this last night.
I always wondered about that when I watched figure
Yep.
skating.
Yeah.
Something I
You just have
didn't
to have your
believe,
weight center
you know?
over your leg then.
Alright.
You ready?
Yeah, I think so.
Alright.
It's kind of nerve-wracking.
It is a little bit. You don't really know. It's neat to get the feeling just for how different it is, and then you can pull them in again. And
Bring out the table.
Okay.
Yeah. And the reason she can get spinning faster is because she is narrower, so it's more focused. Her moment of inertia is.
I can imagine.
Now, I said the goal
That's
of
why-
that was to calculate the moment of inertia using conservation of angular momentum. So, if you remember the ramp part, we use conservation of energy to get the moment of inertia of the wheel. We would use conservation of momentum to get the moment of inertia of the person spinning out there. So, when you had the wheel, you turned it. Initially, there was no angular momentum in the vertical axis. But once you turned it, there was, and that's what caused you to start spinning, so it would balance out. So initially, 0, moment of the wheel plus moment of the person. You can solve this for I, the person, because we're trying to find the moment of inertia, and you would do one last calculation. You would find your